True Projects. In this video, we are going to explain about the project entitled as Enhancing Mobile App Recommendations with Crowdsourced Educational Data Using Machine Learning and Deep Learning. So before getting into the video, let me give you the brief description about the project. This project enhances mobile app recommendations by combining crowdsourced educational data with machine learning and deep learning models. It analyzes users' insights and learning behavior to deliver more accurate, personalized suggestions. The system ultimately improves users' engagement and learning outcomes through intelligent data-driven recommendations. Coming to the abstract explains that as mobile education applications continue to grow rapidly, there is a strong need for smarter recommendation systems capable of offering truly personalized learning experience. Traditional methods fall short because they cannot fully capture the wide range of learners' behavior, real-time usage patterns, and constantly evolving content preference. To outcome these limitations, the study proposed an advanced recommendation framework that uses crowdsourced educational data such as users' feedback, interaction logs, and performance indicators, combining with powerful machine learning and deep learning models. Techniques like collaborative filtering help identify similarities among users. Sentiment analysis extracts meaning and emotion from reviews. And deep learning models such as LSTM and CNN covers deeper patterns in sequential and textual data. By integrating these methods, the system is able to generate more accurate, adaptive, and context aware app recommendations. The results demonstrate that using large scale crowdsourced data meaningfully improves recommendation accuracy, enhances users' engagement, and leads to better overall learning outcomes. Coming to the existing system in mobile educational recommendation platforms mainly depends on simple information such as app categories, basic metadata, and traditional collaborative filtering methods to suggest applications to users. However, these approaches have major limitations because they do not analyze deeper aspects of user behavior or fully utilize the rich variety of user generated content available today, such as textual reviews, star rating, feedback patterns, and activity logs. Most current systems also ignore important contextual factors like a learner's preferred learning style, the difficulty level of content they engage with, their performance trends over time, or how their learning needs change in real time. As a result, the recommendations produced are often generic, one size fits all, and lack meaningful personalization. Additionally, because existing systems do not integrate diverse crowdsourced datasets or apply advanced analytic methods, their ability to adapt to changing user needs and provide accurate, relevant suggestions remains limited. Coming to the proposed system or base paper work. The proposed system is an intelligent and adaptive recommendation framework that uses crowdsourced educational data along with machine learning and deep learning techniques to deliver highly personalized app suggestions. It combines information from user reviews, engagement patterns, learning performance, and peer feedback to build a detailed learner profile. By applying pre-processing, feature engineering, sentiment analysis, and models like deep neural networks, LSTM, and hybrid collaborative filtering, the system identifies hidden user behavior patterns and accurately predicts learning preference. It continuously updates recommendations based on real-time interactions, resulting in more relevant, context-aware suggestions that improve user satisfaction and learning outcomes. Coming to the dataset used in the project is a comprehensive collection of users' feedback gathered from the top 15 globally popular mobile applications, providing a rich source of information for analysis. It includes detailed user generated reviews along with several useful attributes such as a unique review ID, the textual content for each review, the numerical star rating given by the user, and the TU count indicating how many other users found the review helpful. Additionally, the dataset records the app ID and app name to identify which application the feedback corresponds to, as well as the receiver indicating the specific version of the app reviewed. Because it contains both textual and numerical data, the dataset supports a wide range of analytic and model building tasks, including sentiment analysis, rating prediction, user behavior understanding, and the development of personalized recommendation system. It serves as a valuable resource for exploring user opinions, identifying trends, and training machine learning and deep learning models within the project. Coming to the novelty or extension or enhancement or improvement. As an extension to the core system, the project implements a powerful hybrid deep learning model that combines LSTM and GRU architectures to improve the accuracy and robustness of predictions. In addition to building both the existing and proposed models, the project incorporates explainable AI techniques such as line and share, which helps interpret the model decisions by highlighting the importance of individual features in the app recommendation process. This ensures that the system is not only accurate but also transparent and trustworthy. Furthermore, a user-friendly interface was developed using the Flask framework, enabling users to interact while the system directly by entering input and receiving the predictions from the trained models, thereby demonstrating the practical and real-world applicability of the project. Coming to the flow of the work, firstly, importing the packages. This module loads all the required Python libraries for data pre-processing, visualization, machine learning, deep learning, and model evaluation. It ensures that all necessary tools are available before proceeding with any operations. Next, exploring the dataset. The dataset is examined to understand its structure, attributes, and overall quality. This step helps identify missing values, data patterns, and characteristics relevant to app recommendation. Next, data pre-processing. Pre-processing includes creating timestamps, removing unnecessary columns, and applying label encoding to convert categorical data into numerical form. This step prepares the dataset for efficient model training and reduce noise. Next, data visualization. Visualization techniques are used to analyze the distribution of classification outcomes and identify any imbalance or trends. It provides insights into how user behavior and how feedback is distributed across apps. Next, feature engineering. The pivot table is created to reshape the dataset into a format suitable for collaborative filtering models. This step extracts meaningful features relationship that improves recommendation performance. Next, splitting the dataset. The dataset is divided into training and testing sets in 80:20 ratio. This ensures that models can be trained effectively and evaluated fairly on unseen data. Next, build the CF classification model. Multiple collaborative filter algorithms and deep learning models, including SVD, KNN variants, LSTM, GRU, SAE, and GAE are constructed. Each model learns user item interactions differently, allowing comparative performance analysis. The extinction model LSTM plus GRU enhances accuracy using hybrid architecture. Next, training the model. All models are trained using the prepared training dataset. During training, the model learns patterns, relationship, and user preference to make accurate recommendations. Next, comparing the models. Each model's performance is evaluated using the metrics like explained variance, mean absolute error, and root mean squared error. This helps determine which model produced the most accurate predictions. Next, comparing the graphs. Visual comparison graphs are plotted to show the performance of all models side by side. These graphs help easily identify the most effective model. Next, save the trained model. The highest performing model is saved for future use. This ensures that the trained model can be deployed without retraining. Next, explainable AI visualizations. LIME and SHAP are used to explain the importance of features and how each feature influences the model's prediction. This adds transparency and interpretability to the recommendation process. Coming to the front end, the user interface is built using the Flask framework and integrated with an SQLite database for user authentication. This allows users to securely register and log in into Access and recommendation system. The frontend uses the best performing trained model to generate recommendations for users. The interface provides a smooth and interactive experience for viewing suggested apps. User enter feature values or preferences through the interface. These inputs act as a bias for generating personalized recommendation. The user-provided data is cleaned, encoded, and transformed to match the model's expected input format. Proper pre-processing ensures accurate prediction. The pre-processed inputs is fed into the saved trained model to generate the final recommendation. This ensures consistency with back-end machine learning logic. The recommendation results are shown clearly on the front-end interface. This delivers an easy-to-understand output for users based on their input. The algorithms used in the project are SVD, SVDPP, NMF, Slope 1, KNN Basic, KNN with means, KNN Baseline, Co-clustering, Baseline only, Normal Predictor, GRU, LSTM, SAE, which is known as Tagged and Autoencoder, GAE is known as Gated Autoencoder, and as an extension, we have implemented LSTM plus GRU. Coming to the requirements, we have both hardware and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project's code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. The home page of the project should now display in the browser. This is a front-end built using Flask framework. In this page, we have home button and sign up button. Now, click on sign up button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, contact number, and a strong password. Now, click on sign up so that all the given details are stored in signup.db and the login HTML will be opened, where you need to access the application by username and password. Now click on login so that the prediction page has been displayed. In this page, we have prediction button, data visualization button, notebook button, and sign out button. Firstly, click on prediction button so that the personalized app suggestions will be opened, where you need to enter your details to receive intelligent recommendation powered by machine learning and deep learning. So here we have 4 different steps, like first user info, second is rating, third is app details, and fourth it will complete and show you the output. So firstly we need to enter the user ID. Click on next step. Next we need to select the rating. Then click on next. Then we need to enter the application identifier. Click on next. Next we need to enter the date and time. The format of date and time is clearly given here. Then click on get recommendations, so that the input is pre-processed and the output is displayed like your input information, like we have given the user ID is 4, input app is 654, the rating will be 3.0 and the timestamp is also given. For that, the top 5 recommendation educational apps are like Android, Lemon, Roblox, Instagram, Kilo. And here we have how it works and the rating interpretation. Then click on get new recommendations so that again you can enter the input details and predict your output. Now click on data visualization so that the graphical representation of the projects will be now displayed. First we have data distribution graph. The pie chart shows the percentage distribution of total app scores across 5 categories labeled 1 through 5. Category 1 has the largest share at 42.1%, indicating it contributes the most of the total scores. Category 2 is 15.1%, 5 is 14.9%, and 3 is 14.0%. Each hold similarly mid-range proportions, showing they contribute moderately. Category 4 has the smallest portion at 13.8%, making it the least represented. Overall, the chart highlights a strong dominance of Category 1, while the remaining categories are relatively evenly distributed. Next, we have frequency of applications graph. The bar chart shows the total number of times various applications are used, highlighting a clear difference in usage frequency across the listed apps. Facebook stands out dramatically with around 2000 users, making it to the most frequently used application by a large margin. All other apps including Instagram, Telegram, Zoom, Snapchat, Spotify, Roblox, and others have similar usage levels, each at roughly 1000 users, indicating a relatively even distribution among them. Overall, the graph emphasized Facebook dominant usage compared to the rest, which maintain consistent but lower frequency. Next, we have correlation heat map graph. The heat map displays the correlation between rating and app ID. using custom colors to highlight the strength of their relationship. Both variables shows a perfect self-correlation to 1 as expected. The correlation between rating and app IDs is 0.20, indicating a very weak positive relationship, meaning that changes in app ID have little to no meaningful connections with changes in rating. Overall, the heat map visually emphasizes that the two variables are largely independent of each other. Next, we have RMSE score graph. The bar chart compares the root mean squared error of various recommendations and deep learning models, with lower values indicating better prediction accuracy. Traditional collaborative filtering models such as SVD, SVDPP, NMF, and KNN variants shows moderate RMSE values around 1.3 to 1.5, while baseline and clustering methods perform slightly worse. In contrast, neural network models, particularly GRU LSTM, hybrid LSTM GRU architectures, and their mean variance achieve significantly lower RMSE scores, indicating much stronger predictive performance. Overall, the graph highlights that deep learning based models substantially outperform classical recommendation algorithms in terms of accuracy. Next, we have MAE score graph. The bar chart displays the mean absolute error of a range of recommendation models, where lower MAE value indicates more accurate prediction. Traditional models such as SVD, SVD-PP, NMF, Slope 1, and various KNN-based approaches show moderate MAE level around 1.1 to 1.4, while baseline and clustering methods perform slightly worse. Similar to RMSE results, neural models including GRU, LSTM, hybrid LSTM GRU architectures, and their mean variance significantly outperform the traditional methods, achieving very low MAE values. Overall, the graph highlights that deep learning based approach deliver far more precise predictions compared to classical recommendation algorithms. Next, we have explainable AI water plot graph. The chart compares to be a feature importance of sharp style explanation plot showing how different input feature contributes to a model's prediction, where the horizontal bars represents each feature's impact on the output. The item labeled item 0 through item 8 all contributes positively and almost equally to the prediction indicated by the similar bar lengths on the right side. In contrast, the group labeled 5 other features has a negative contribution shown by the blue bar extended to the left. The overall prediction values is around 0.003, suggesting the positive and negative influences nearly cancel each other out. Overall, the graph highlights that the 9 item related features dominate the prediction, while the remaining features collectively reduce the predicted value slightly. Next, click on sign out. So finally, the project shows that combining crowdsourced educational data with machine learning and deep learning significantly enhance the accuracy and personalization of mobile app recommendations. By leveraging diverse user input and advanced models, the system overcomes data sparsity and better capture real learning needs. The resulting recommender improves user engagement and offers a more adaptive, effective educational experience. So this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.